Okay, welcome. This is the module 5, basically the last week of blast furnace iron making, and it is also the last part, one lecture on the blast furnace iron making, and then we'll move to the steel making and finally the alternative routes of iron making. So anyway, so this is the lecture number 24 and I will talk about the modeling of blast furnace very briefly. Okay. And two modeling aspect I will discuss. One is the thermodynamic modeling and another is the transport phenomena based phenomenological modeling. Some of the modeling has been done already. A few examples I will just try to give from this. Now first let us talk about the thermodynamic modeling. And what do we mean by thermodynamic modeling? As the name suggests, you assume the reactor in thermodynamic equilibrium. And then you can apply some thermodynamic database like Faxage and you can calculate what will be the output, what will be the phase constituents at equilibrium, temperature, if you want to calculate the heat of reaction, all these things are possible. So basically thermodynamic model can capture the saturation level of the product. That is, it doesn't consider about the kinetics of the process, like how the phase evolves with time or interaction between the phases, and during the process whether the phase will attain thermal or chemical equilibrium with or not, it doesn't consider all these things. What it considers is that everything has attained an equilibrium and then it calculates the saturation level of the phase constituents, etc. Okay. So that is the thermodynamic model, but sometimes it has been found, and if we can do a multi-zone thermodynamic model, that means if we divide the whole calculation domain, whatever it think about, or the reactor into number of reactors and connect it by input-output flow, one reactor to another reactor, then it moves little to the real situation. Okay, because otherwise, as I said, thermodynamic model doesn't capture the transient phenomena, and during this process, that is the actual process, whether the phases attain the thermal equilibrium or not, it may not be. So mostly in some cases, there is a thermal equilibrium is not attained, but it can calculate only the final, that is the if it attains an equilibrium, what will be the final composition. Okay. Now I will talk about an example of a thermodynamic model, multi-zone thermodynamic model, that is the blast furnace. You can conceive into a number of equilibrium reactors. Okay. And then you can connect this reactor by input and output stream, okay, solid stream, gaseous stream, and then you can predict the that is the final product composition like hot metal composition, slag composition. You can also calculate what will be the coke rate, you can calculate exit gas composition, all these things. And also in this thermodynamic model, we have some option of splitting the gas. That is because all the gas during this, because when the gas solid interaction is taking place, you cannot assume there is the all thermal and chemical potential of the gas has been completely utilized. A part of the gas will move is some amount of heat as well as some amount of the CO along with it, which will not interact with the gas because it doesn't have sufficient time for interaction. All the gas constituents cannot sufficient time for interaction. So we can bypass a certain fraction of the gas to the upper reactor without participating in the reaction, and as a measure of deviation from the equilibrium. Okay. Now first let us discuss this thing. This thing you can see we have some reactor like reactor A. A is basically an adiabatic reactor. Adiabatic reactor, basically the ratio you can model like this, and what you are doing here, basically the coke that is coming, here there is a splitter, you are splitting the coke, a part of the coke you are giving into this adiabatic reactor, and a part of the coke will go directly to a direct reduction, a reactor, it is the reactor for direct reduction. Okay. So I will come to that thing, and then this coke will be burned in the reactor A, adiabatic reactor, and generating heat, and you can calculate the heat generation from simple form heat of reaction. You know, basically the Faxage from FACSAGE is a very good thermodynamic database, and using the FACSAGE you can calculate what will be the total heat effects, and you can also calculate what will be the final composition of the gas. What you are giving, basically you are giving the coke, partially some coke, and also you are giving some humidified blast also, and some oxygen enrichment. So, some oxygen enrichment you are doing of the air blast, and humidified air blast are also giving. So, you are giving the blast along with certain amount of oxygen, little bit, that is the usually it is 21 volume percent oxygen, you can make it 23 or 25% oxygen. Also you can give some amount of moisture into the air blast. So, air blast is coming, coke is coming, and then you have an adiabatic reactor. So, by FACSAGE you can calculate what will be the total heat effects, what will be the temperature of the gas, and what will be the final composition. Okay, final composition obviously it will be the CO gas, and if air blast, so nitrogen will be there. So, this composition you will get. So, this CO and nitrogen will enter into the reactor B. Reactor B is called the reactor for direct reduction. Okay. Basically why I am calling, because it is a high temperature reactor. So, you can give a certain amount of coke will participate into the direct reduction. So, I am splitting here the coke. So, I am giving certain amount of coke, but how much coke I will give from the direct reduction, that has to be estimated by iterative method. I will come to that. So, I will carry out some amount of direct reduction. Basically here you will get the Woostide only. So, a part of the Woostide will be directly reduced, and part of Woostide will be reduced by, that is the CO gas that is being generated into the gasifier and coming here. So, that also react into indirect reduction. Okay, and some direct reduction will be there. And finally, this gas stream obviously now you have CO and CO2, now it is no more CO and CO2 will come, and then it will enter into the chamber C. This reactor, C is a reactor for indirect reduction of Woostide, right? And here whatever the gas is coming and splitting, you can find a part of is directly that is the going to the, that is the reactor E, where basically final gas composition reactor. So, this CO will not participate into the indirect reduction, because it happens because of kinetic consideration. So, a part of CO I am taking off, okay, and it is basically calculated based on the shaft efficiency of the reactor of the blast furnace. If you know the shaft efficiency, that is the CO utilization, basically from there you can estimate, that is the how much you will take it out. Okay. So, this is one part, and then this is the reactor C, where indirect reduction of Woostide will take place. From here the gas stream, red is the gas stream, that is the CO gas is going here, and from there what it will come here, that is the Woostide will come out, part of the Woostide will come out here, and also the flux that is coming along with it. So, Woostide will come here and the CO gas is going. Partially reduced Woostide, because the Woostide partially will get indirectly reduced, and then whatever the Woostide is left out will come here, and it will be finally directly reduced, or part may be indirectly reduced because of adiabatic gasifier, whatever the CO you are giving, this CO may participate into the indirect reduction. So, and then from here what you are getting, whatever the CO gas, that is this reactor, this thermodynamic reactor also it will come to an equilibrium. Here obviously if you Woostide equilibrium you will get, so O by C ratio will be, you can understand what will be that thing, that is your 1.3. So, from here there is the CO gas will come and it will join the D reactor, and from here in the D reactor basically higher oxide reactor for the higher oxide, reduction of the higher oxide indirectly, and so here Fe2O3 will convert to magnetite and magnetite to Woostide, and whatever, and output of the D will be the Woostide only. So, Woostide will come here, and from there the CO gas will move out, right. After thermodynamic equilibrium here it will move out here. Okay. So, this is basically CO plus CO2. CO plus CO2 will attain here. Obviously, the CO-CO2 ratio in this reactor will be 1.3, and then CO-CO2, moles of CO and CO2, whatever that is composition you can detect from this reactor, and that will join here, and the Woostide will come and join the C reactor, and this reactor D reactor basically higher oxide reduction. So, you can find the reactor D will get an input of dry burden. It is the dry moisture. I have taken it out separately here. You can find This is the moisture here. So, it is the dry burden at 25 will enter. So, then in this reactor no moisture will be there. So, every dry burden will react with the CO2 and it will be reduced to hematite magnetite to woostite, and woostite will come and it will be an input for the reactor C. So, this you can find. So, from the burden we have taken out the moisture. So, you can find here is the moisture and there is a mixture. So, whatever the CO bypass CO as well as the CO2 mixture from the D will come, equilibrium CO2 mixture from D will come to this reactor, and the bypass CO will also come, and also the burden moisture will be mixed up, because it is a mixture, you can find it will be mixed up, and then it will come to a thermodynamic equilibrium. And this reactor is basically for an water gas shift reaction. Here basically CO may react with the moisture forming the CO2 and H2. So, and finally you will get the blast furnace gas composition, and which will come out, right. At temperature, which temperature also this thermodynamic reactor will decide. There is a, based on this calculation you know what will be the exit gas temperature, what will be the composition, all these things. So, this reactor basically are calculated using the FACSH simulator thermodynamic software for all reactor gas composition, and the temperature you can calculate from that software. Okay. And finally, you can get the hot metal composition, slag composition also out of this, and that will be also calculated by FACSH. And finally, as I was telling that here the coke is basically splitting into two parts, coke 1 and coke 2. So, how much for the direct reduction and how much for the indirect reduction. So, that amount of the coke, the splitting will be decided by some marker stream, solid stream, right. Or maybe that is the iron, how much you are getting, you are giving the Fe2O3, how much moles you are giving Fe2O3, double of iron will be produced, or you can get the FeO, how much FeO from there will be produced. You can fix that when that amount is getting fixed. So, you can know that this is the mass balance something, that is the iron, basically whatever the, that is the some solid stream marker should be there. If you give this much of Fe2O3, you must get this much of iron, whether you are getting it or not. So, when it is fixed, then you can that is the way you can stop it. Okay. So, iteration. So, iteratively you can calculate what will be the partitioning of the coke for direct and indirect reduction. So, this is a simple thermodynamic model, and it can be further be complicated, but it is based on the work of the Swayam Prabha and his MTech thesis at IIT Kharagpur, and this is, and the comparison with the RIST model you can find, there is the simulated value of the coke rate and the RIST diagram value also. From this diagram, if you know the oxygen blast, and also if you know the thermal pinch point in the RIST diagram, you can calculate the coke rate. This is the coke rate and the simulated value is there, and for different data set you can find this thing, and there is a quite match between these two. Also the O by C in the exit gas also you can find a very close match. So, this model is working. So, now if you want to predict the hot metal and the slag composition also, you can see that is the percentage carbon in the hot metal. You can see there is a close match with the different data set. There is a quite good match is there, percentage silicon also good match, and it is the basicity of the slag you can see for different data set, and percentage of sulfur there is a slight difference is there you can find here. So, this thing that is the thing, and basicity of the order of 1 is there, but sulfur prediction has been little off, otherwise everything is okay. Now, transport phenomena based model, next I will discuss. So, thermodynamic model you can quite reliably predict the hot metal composition, carbon rate, exit gas composition and temperature, everything you can predict quite reliable using this multi-stage thermodynamic model, right. Now, what I said is that it is little different from the phenomenological model. So, it does not give any idea about the phenomenological thing or the phenomenon that is happening during the process. For understanding the process, you require a phenomenological model, and also for capturing the transient phenomena, you require a phenomenological model. So, this is basically mostly the transport phenomena based it happens, and I will basically discuss actually two types of models are there. One is continuum based approach, and this is called in blast furnace 2 fluid or 3 fluid model, because in case of the continuum there is all the solid, that is the coke, iron ore, flux, all the solid is considered as a one continuum phase, that is it is basically treated as a fluid with a higher viscosity like that. So, it is a great assumption in the continuum based model because without that it cannot do. So it may be a 2 fluid, 3 fluid model depending on the blast furnace, but it is called the continuum based approach. Another is the discrete phase model, and it is based on the discrete element method in the main level model that is available in the commercial software. The discrete phase model, what happens is that here basically you treat each, you make a force balance on the each particle. Basically you track each and every particle separately. So, and then you know where it is going, what is its position as a function of time in the reactor, you can find out. So that gives a more realistic, and it can be also a transient. With time you can evolve, and continuum based model is mostly the steady state problem, and this is discrete phase model in the blast furnace is transient phenomenon. Complete blast furnace model has not yet been achieved. So these are the two models are there. One is continuum based and other is the discrete phase model. And here basically you track each solid particle separately, okay, unlike into the continuum based model. And complete blast furnace model has not yet been achieved. If you see the blast furnace, as we have said also earlier, basically it has a lot of different zones are there, and then so far the whatever the model has been made, in the you have a charging system is there, okay. So there is a place for modeling. You have a raceway, you can separately model it. You have a hearth and the dead man coke, whether sitting dead man or floating dead man, on all these things. It is acts as a porous medium, coke bed is there. So there is the chance of modeling in the hearth and tapping and all these things. And other thing is the body. Actually, the modeler has divided the blast furnace in these parts. These are 4 parts. One is the charging, another is the raceway, hearth, and the final is the body of the furnace. In the body of the furnace, it includes all the granular zone, that is the solid gas interaction, cohesive zone where the softening takes place, dripping zone. So all these zones are considered in a model that is called the body. Okay, so separate models are there basically. So, and then in case of for the main body modeling, that is when you consider all these zone main body modeling, your input is charging. There is a charge distribution, there is a stock line distribution is the input, and that you can get by modeling the burden distribution. And then raceway also another input, what will be the gas temperature and what is the gas flow rate, everything you can take it as an input from here. And then the hearth, there is the metal tapping, that is an output you can take as an output, and then you can model that is the main body. So this is the way basically it has modeled it, okay. But a complete modeling of the blast furnace has not yet been realized. That is by integrating all these raceway, hearth, and the charging and the main body, all this integration, and finally it has not been done. So, and the brief description of the model, first is the continuum based model. As I said, the continuum based model that exists in the blast furnace is steady state model only, and also consider the solid as a continuum, okay, another fluid with certain higher viscosity, and conservation of mass, momentum, heat and mass equation are solved in 2 fluids, taking into interaction between those. This is basically the equation of, that is the conservation of mass, continuity equation, and this is there is the momentum equation, 3 component of momentum, as well as you can have other equation like enthalpy balance and the mass balance, species balance equation will be there, and if you want to solve in turbulent K epsilon model, all will be there. But discrete particle model, in this case what happens, you basically make a there is a momentum balance in each and every particle. So momentum balance is done on each and every particle. What are the components? There is the acceleration, and this is the translational momentum, and this is the angular momentum, okay. So m into d by dt, that is the translational, that is this is the rate of change of you can find there is the force balance, simply it is for the translational velocity of the particle, and what are the there is the acceleration is equal to mass, there is the force basically as mass into acceleration is equal to second law of Newton, Newton's law of second law of Newton, and then you can find this is basically the summation of forces. And what are the forces you have? Fc, basically you can see Fc, Fd and Fsl. Fc is the force due to elastic contact. When 2 particles come in contact, they can exchange the energy elastically, that is without any dissipation, then elastic force. and then viscous contact, and that is basically damping force. If you have some viscous, that is the resistance, frictional loss basically, that is by the viscous contact, okay, and the solid fluid contact, and that is another drag force, that is also coming, solid fluid contact. So drag force, and then your viscous damping force and the elastic force, these are the summation of the force plus the gravity force, okay. That will basically dictate how the particle will accelerate, okay. So that is the from second law of motion, basically Newton's second law of motion, and this is for translational velocity and this is for angular velocity. So angular velocity, the formation of force is basically the torque. One is the tangential torque, another is the rolling friction, due to rolling friction. So this is basically what I want to mean is that basically single particle, that is each and every particle undergoes a force balance, and then we can predict their location at different parts of the their location and time. This correlation we can make, time versus location, okay. So that is the discrete particle model. But here one thing is that can describe the transient behavior, that is most important. In blast furnace, how the cohesive zone evolve with time, etc. This thing you can describe the transient behavior. But another thing is that it's computationally expensive, especially if you want to do force balance in each particle, then there may be billions of particles, very, very large number of particles into the blast furnace, and for each and every particle we have to solve this equation. So it becomes computationally very expensive, okay. And now I will just give some example of the modeling example what has been done. First we will start with the wear of Hart refractory model based on the continuum model, and it is called the inverse model. What is called an inverse model? Basically, when we want to predict some input condition based on the output condition, okay, that is called the inverse modeling, by matching the output condition. Suppose you have experimental and the predicted output, you can match. If they are not matching, then you can do trial and error or apply some optimization tool to fit the certain input condition such that this output from experiment and the model matches perfectly. So that's why that is the based on the output you can predict the input also, that is called the inverse model, okay. So in the wear of Hart refractory, you can calculate by the wear model, and basically here is two model, basically two conjugate model you solve simultaneously. One is the one dimensional transient heat transfer model in the brick, refractory brick, this is the carbon brick, okay, that you do, and with a moving boundary, because sometimes you have the skull formation on the refractory wall also, that's why we do some moving boundary one dimensional transient heat conduction model. And the wear profile is basically calculated, it is taken as the 105 degree centigrade isotherm, that is basically the solidus of the FEC system, iron carbon liquid, okay. So that is the why there is the at the temperature, because at the saturation level, when the carbon is saturated, the liquidus of the iron become very low, 1050 we have taken at very high concentration of concentrated carbon. So this is basically the liquid will solidify at this temperature. So that is the brick wall, you can say, adjacent to the brick wall. And actually some amount of skull formation may be there. And then we can find out what is the refractory location, because the skull will be very low conducting compared to the carbon. As a result, isotherm will be very fine in the skull region. So we can understand where is the skull and where the refractory, okay. So basically the wear profile can be calculated, can be obtained by adjusting the predicted and measured temperature in the refractory wall, as I said, by inverse modeling. And also you have another model, a three-dimensional CFD model is used to calculate the velocity inside the heart. And heart, basically you know all the dead man cokes are there in the heart, either they may be sitting or they may be floating, okay. And but you can do this in case of the continuum model. What you have to do, you have to consider a fixed shape of the that is the, what is that called, that is the dead man coke, okay. So either you consider a sitting dead man or a what is that, floating dead man, and then you take a pre-assumed shape of the coke bed. You have to take a pre-assumed shape, and then you have to consider it as a porous medium, and then the liquid as a continuum phase, okay, you can solve it. So A three-dimensional CFD model is done to basically to calculate the temperature distribution in the liquid, okay, and it is solved in conjugation with this with this one-dimensional transient heat transfer model in the refractory valve, and by inverse modeling you can calculate the wear of the refractory. So you can find that is this is the predicted wear profile with a skull. You can find here this is a wear of the carbon refractory. You can find it has significantly wear here. And if you see, if you can just, it is not possible to increase because of skull. You can find in this location the temperature contours are very close together. Okay, so we can understand some amount of skull is there. Skull is there. After that, this is the wear line. Okay, and this is a very important phenomenon. That is, if we can, because it is very opaque system, so we cannot see the wear of the refractory. But understanding the wear life is very important, because if the refractory line wears very fast, then the blast furnace has to be stopped. So health monitoring and then taking the appropriate action such that this wear do not propagate very fast is very important. So from that point of view, this type of modeling is very helpful. We can understand the health of the wear of refractory lining and we can take some precautions. Okay. So it is reliably has been modeled, and lot of mathematical validation. There is the experimental validation also there available in the literature. So now some other results from the CFD DEM model. I am just showing you from DEM model, basically what you can do from DEM model. You can see this is the predicted, this is the continuum model. I should talk about this continuum, and this is some example from the DEM, CFD DEM. So here you can see we can calculate the velocity of the particle. So you can see the velocity of the particle become maximum in the center, and then periphery it is less. Okay, and as you move towards the much deeper, the velocity slowly decrease. Okay, and here the porosity distribution is also there, but not very clear here in this figure anyway. And this is the cohesive zone. Cohesive zone prediction is quite very nice. And the first figure is basically infinite state of cohesive zone from the dissection. Basically, it is basically done in a Sweden MEFOS laboratory, LKAB laboratory, where the experimental blast furnace is freezed by liquid nitrogen, and you can take the dissection, and the cohesive zone is found like this. And you can find this cohesive zone here. Basically, the liquid formation is taking place. That's why it is black. You can find. So this is the cohesive zone. Okay. And this is the model predicted from the DEM model, and you can see this region, white region, is basically the softening region. So you can find a very close match of the cohesive zone. And in this region, coke is there, that is basically not shown. And you can also calculate the temperature distribution in this by main model, and it is for the gas and it is for the solid. So you can know what is the temperature, complete distribution of temperature also can be known from this model. And it is a burden distribution model. It is also in this area the DEM has made a very great progress. And this is one picture. You can see the color map of discharging time of particles during the hopper discharging process. So basically this particle will come first, there is the red will come first within 0 to 34 seconds, and then this green particle will come out next, the 34 to 68 seconds, these will come, and then the blue one will come in 68 to 102 seconds like this. This will be the 102 to 136 seconds, and this purple will come at the end. Okay, so this is the way you can know that is the when the particle is coming out. And obviously, as I said before also, because of a velocity profile, basically the velocity near the center will be high and the fines will be dragged near the center and the coarser will be away from the center. And they have also calculated the diameter from the discharging time. You can see initially all the fines are drawn. That's why you can see the fines. The fines are drawn because here along the central line, there is a lot of fines will be there. So fines are drawn first, so the diameter is less, and then with discharging time, then the coats are appearing. Coats will be appearing, and then finally again the fines will come. Okay, so that is the way there is the hopper discharging. When you discharge from the hopper, what type of particle distribution you will get? It has been perfectly been modeled by the DEM model. Okay, so So that has been done. And now I'll give you some example of stock line segregation by mechanistic model, that is this thing. And here also you can find, that is in this diagram what you can find, it is the inner and outer trajectories of the solid discharge at various chute angles from the rotating chute. Basically, when the particles are there in the rotating chute, they are under the action of drag force and then centrifugal force. All these forces are there because of movement of the reference frame. So Colliory's force, okay, so those are the forces are there along with the drag and the inertial force. And finally, when the particle fall, they are also under the action of inertial force, that is the which is generated from the chute, and then they are under the action of gravitational force as well as drag force. So finally, the projectile fall on the point of impact on the stock line. And then using this model, this Das et al. Have been able to calculate what will be the inner and the outer profile of the trajectories. As I basically the outer trajectory where basically lighter and the bigger particle will move, and the heavy and solid particle will move through the inner trajectory. So all the solid will basically be fall within this outer and inner trajectory. Okay, so you can calculate where the particle will fall in the stock line, right? And based on that, you can generate the stock line profile also. And here you can see the stock line segregation, that is here basically the predicted particle size distribution, okay, of the burden materials for 4 different locations in the stock line. That is, one is that at the point of impact, and this thing they have calculated with the MTA, basically movable throat armor if you used, and then when the particles are coming from the bell, top bell, and they are hitting at certain location, okay. So at the point of fall, the size distribution is like this, given by the dark line. You can find they will form the fines are there. Most of the fines they accumulate at the wall, okay, and then the particle it is decreasing. You can find it is decreasing from it, okay, the particle size. So at the point of fall, you have the smaller particles are there. Most of the smaller particles will accumulate at the point of fall, and most of the bigger particle will roll down away from it, right? So that it is showing. And then if you see, if you go away in the radial direction, say 1 meter, 2 meter and 3 meter, and then this segregation is decreasing, that you can sign there's a fine segregation are decreasing because the peak is going down as you move away from the center. So this type of size segregation also you can predict based on this mechanistic model, that is if you make a force balance on the particle, right, during their flight in the air, also during in the rotating chute, if you just make the force balance considering all the available force application on that, and then finally where the particle will fall, where, which location, what, and the segregation, all these things is possible to calculate, okay. So this is, and some references we have considered, these are all the references. And so conclusion I can say, there is a multi-zone thermodynamic model with certain bypass of solid and gaseous stream can predict the coke rate as well as the slag hot metal composition quite reliably. Okay, it's the multi-zone thermodynamic model, and also by taking some bypass of the gas and solid stream to consider, that is the kinetic aspect, that is the kinetic effect. Okay, you can have some amount of, as I shown you, some kind of gas bypass we have taken to make it more realistic, right? So that type of assumption if you make, and then we have seen finally that the slag and hot metal composition prediction is quite good, okay, and so the coke rate prediction also quite good and matches with the risk model also. Okay, 2 types of phenomenological models. These phenomenological models are important, as I said, for understanding the transient evolution of different process and phase into the reactor, and also to estimate the time, okay, or to estimate what will be the actual phase composition at a particular time into the reactor, okay. So this 2 types of phenomenological model we have discussed. One is the continuum based, and another is the discrete particle based. And burden distribution, temperature profile, cohesive zone, health, wear, There is the hearth wear profile have also been predicted quite reasonably, we have seen. And DM model can simulate transient behavior, that is very important, but at the same time those are computationally expensive, while continuum model are basically widely used today also, and these models are steady based on steady state, but it is also makes some simplistic assumption. But DM may be little cost effective, but it predicts more reliably, that is its predictions are quite good. And finally, the thermodynamic models also one can use most reliably into the steel plant also, thermodynamic model, especially the multi-zone model, and taking into aspect some of the kinetic aspects like shaft efficiency, all these things which we can consider by bypass of the solid stream, all these things we can measurably, reasonably calculate the output parameters. Okay, this is a very brief about the mathematical modeling that has been done on the blast furnace. Obviously, author can, that is the reader, can go through all the reference that I have given and have a better feel about the mathematical model into the blast furnace. Thank you very much.